Anyone remember those three factors of mean arterial pressure? Perfect, yes, stroke volume, heart rate, and resistance, total peripheral resistance. Thank you, that's correct. And then we also looked at cardiac output, which was a product of stroke volume and heart rate as well, okay? Okay, let's look at a few checkpoint questions here, and then we'll do a bit of review in terms of that baroreceptor reflex. And then I do have some additional polling questions just to make sure we understand that regulatory part of mean arterial pressure, and then we'll finish up with this packet, okay? So quite a few things to do here today. So let's start with these questions, and I'll give you a second to kind of look at these. And again, when we go through these checkpoint questions, really try to write down a response. It's really going to help clarify your understanding, and then it's going to serve you when you go back and look at these later on, okay? So although, okay, yep, so try to make sure you're writing a response, whether you're verbally sharing one or not, okay? So question one is, what is a baroreceptor? So what is a baroreceptor? Perfect, yes, it's a pressure receptor. That's probably the simplest way to put it, because there are two different types of baroreceptors. So yes, it's a pressure receptor, and it is one of the sensory receptors that picks up changes to stretch in the walls of certain structures, right? Let's look at number two. Where are the arterial baroreceptors located? So we spoke about the arterial baroreceptors, which were more specifically called stretch receptors, and they were found in two spots. Perfect, yes. Also in the chat here, the aortic arch and the carotid sinuses bilaterally, right? So that's correct as well. And so those are the two spots where we have the arterial baroreceptors, more specifically referred to as those stretch receptors. They're detecting changes in pressure and then sending those signals to the brain accordingly. But we also have what we call low pressure baroreceptors. So slightly different, also in slightly different spots. And you remember where these were located? And then what these were also referred to. So the low pressure baroreceptors. Yes, these were also referred to as volume receptors. Excellent. And that's because of their strategic location. Yeah, they're in the vein, some, but then more so in the atria, right? The wall of the atria. And that makes sense, right? The atria are the filling chambers that receive inflow from the veins. And so having them on those two spots would also make sense if they are detecting low pressure or volume, okay? So those low pressure or volume receptors on the atria as well as the veins. And then number four, what is the baroreceptor reflex? What is the baroreceptor reflex? And this is a bit of a complex question. We're actually going to review this coming up. But generally, what is it serving to do? What is that reflex about? Okay, so I'm seeing quite a few different responses here. So decreased blood volume. So that could be one of the responses, right? If we had a stimuli that increased mean arterial pressure, the baroreceptor reflex would serve to correct that and decrease blood pressure. Other responses here compensate for changes to blood pressure, which is correct, and then make up for changes in blood pressure. Excellent. So we thought about two, totally different opposite scenarios of increasing blood pressure. So think about chronic hypertension or just having higher blood pressures. The receptor reflex would serve to lower that. And then more imminently dangerous, more of a threat to our existence really, are lower pressures. So hypoxia, shock, hemorrhage, those types of changes, the baroreceptor reflex would serve to increase mean arterial pressure, again, in an attempt to correct or compensate or make up for any of those blood pressure changes. Okay, so it's really a homeostasis mechanism. That's why it's associated with that negative feedback loop. And it really serves to keep our blood pressure constant in the face of any type of external change. Okay, all right, excellent. So let's kind of review the components, if you will, the example that we looked at in terms of decreased mean arterial pressure and the several different components, the arteries, not arteries, but the arterioles, the veins, and then the autonomic nervous system, and how the different areas or the different components of homeostasis, such as the sensors, detectors, the integrating center, the effector organ, how those play a role in this baroreceptor reflex, okay? So how do we regulate mean arterial pressure? And we want to remind ourselves that the formula or the relationship of mean arterial pressure is cardiac output times total peripheral resistance. And then we also substituted out for this value or this variable, stroke volume and heart rate. So our three factors that influence mean arterial pressure are stroke volume, heart rate, and total peripheral resistance, okay? So let's look here at the baroreceptor reflex. And how that serves to regulate mean arterial pressure. Okay, so let's start with our scenario of a drop in mean arterial pressure. And I want you to be also thinking about this in the reverse. So if we had the opposite scenario, excess mean arterial pressure, we would have all of the following activities and events in the opposite direction. But our example here is a drop in mean arterial pressure, which is recognized as hypotension in the body. Hypotension, okay, low blood pressure. And so that's going to be detected or picked up or sensed by our baroreceptors. Specifically, our stretch receptors are arterial baroreceptors, the ones in the aortic arch and the carotid sinuses, okay? Now, the next step here is that that's going to send a signal to the integrating centers. We spoke about these being in the medulla oblongata, central nervous system structures. Okay, and then the integrating centers are going to analyze this change and determine what is going to correct this change. And then it's going to send a response out via the autonomic nervous system, okay? And so integrating center sends a response out via the autonomic nervous system, which is really acting here as our effector organ or effector tissue. And let's look now more closely at some of those responses. So we've got two general divisions of the autonomic nervous system that respond. The first one is the parasympathetic system. And so I want someone to tell me what response to the parasympathetic system would correct a drop in mean arterial pressure. Would I increase parasympathetic response or would I decrease parasympathetic response? I'm seeing increase as well as decrease. So quite a few responses for decrease, and decrease is correct, right? Think about what the parasympathetic will do, right? First of all, it doesn't have much of an effect on our arterioles or veins, but it does have an influence on the heart rate, right? And if we go back to our initial equation here, we would need to increase heart rate in order to increase mean arterial pressure, which is the response we're trying to bring about. And so in order to do so, in order to increase that heart rate, we would have to tone down the parasympathetic influence, okay? So we want to tone down or, decrease the parasympathetic output, and that would result in an increase in the SA and AV nodal firing rate, okay? So that's going to cause an increase in the SA node and the AV node firing rate. And that is going to cause an increase in heart rate, okay, which we know is one of our variables up here that we're trying to increase in an effort to increase mean arterial pressure, okay? Hope everyone is still with me with this one. So we increase SA node, AV node firing rate, that increases our heart rate. So that's one part of the equation here. Let's look at what happens to the other part of that autonomic response. So the second part of this autonomic response is the sympathetic division, right? So the sympathetic nervous system, or the sympathetic output. And so if we tone down parasympathetic, it would only make sense that we tone up or increase our sympathetic outflow. And we know that the sympathetic system has a more involved or a more extensive role in this reflex, right? It's going to have an effect on several different components. So the first one is that it's going to also work to increase heart rate. Okay, so it's going to cause an SA node and AV node firing rate to increase as well. And that would work in concert with this, right? So toning down parasympathetic, toning up sympathetic, both have the same response, increasing the firing rate of our pacemaker cells there and causing an increase in heart rate, okay? Now, the other three components of the sympathetic nervous system, one had to do with the contractile cells in the heart. So we're going to increase the ventricular contractility and what is that going to influence? Which of our variables is that going to have an effect on? If I increase how hard the heart is working, which of our variables will that have an influence on? So I'm seeing cardiac output, which is not wrong, but which of our further factors of cardiac output specifically? So cardiac output is not a wrong answer, but more specifically, stroke volume. Excellent, thank you. Stroke volume. So stroke volume, which remember, stroke volume is the amount of blood ejected from the heart. And so if I increase how hard those contractile cells are working, I'm going to increase stroke volume, okay? So that is the variable that we influence by increasing that ventricular contractility. And then the other two responses here are basically what happens to smooth muscle. So it's kind of a twofold response. What happens to smooth muscle? And so this is going to be the influence of norepinephrine binding to our alpha adrenergic receptors and what that does to the state of smooth muscle in two areas. Remember, we have smooth muscle in our veins, a small amount of smooth muscle in veins, and then we've also got a lot of smooth muscle in arterioles. Okay, and so it's going to bring about an effect in both of these areas. In veins, it's going to increase what? when I increase the contractile state of smooth muscle in veins, what is that response called? Or what is that action called? So I'll say that again, increased contractile state or contraction in that smooth muscle within our veins. What is that response called? Excellent, venomotor tone, excellent. So I'm going to contract smooth muscle in the veins, and that is going to increase venomotor tone. Okay, perfect. And then venomotor tone does what to venous return? Yes, that's going to increase venous return. So venomotor tone, putting slightly more pressure on the blood and veins, which is decreasing their compliance. So remember, remember to make that connection. They're slightly decreasing the compliance by increasing the contractile state of the smooth muscle inside our veins. And that is going to aid with the venous return. So we're going to increase venous return here. In other words, how much blood is going back to the heart. And that is also going to favor an increase in stroke volume. Remember, if the heart can fill more adequately, it can also eject more adequately. So there are a couple of steps in here, right? We're going to increase end diastolic volume. We're going to increase end diastolic pressure, and then we're going to increase stroke volume. But this change is also going to work in favor of this variable, this increase in stroke volume. And then as far as the arterioles go, we're going to also see an effect here brought about by, again, norepinephrine binding to alpha adrenergic receptors. On most tissues, that's going to cause vasoconstriction. Remember? So vasoconstriction. And that vasoconstriction is happening on most tissues. I'm going to put in brackets here, except what structures? What structures are exempt here? So brain is exempt, but more specifically, which structures are going to receive that increase, that vasodilation rather? Heart, right? Heart and muscle are going to see vasodilation, whereas brain is going to be exempt from vasoconstriction. So it's kind of a split answer here. So vasoconstriction is going to happen except heart and muscle. Right? In heart and muscle, we're actually going to see the opposite. We're going to see vasodilation, but then brain is not going to have vasodilation. It's just going to maintain its supply. So we can say except heart and muscle, and then I'm also going to put brain here, but understand how brain differs from the response happening on heart and muscle. Okay, we kind of talked about this earlier. And so what is this doing? What is vasoconstriction of arterioles bringing about? Which of our variables here at the top again? If I'm causing vasoconstriction of arterioles to most of my tissues, what is that doing? So I'm seeing stroke volume, so not necessarily, not stroke volume. TPR, excellent. I'm seeing TPR in the chat here. That's going to be, remember, total peripheral resistance, mainly found in arterioles. That's the variable that we're going after here. So causing vasoconstriction on most of our arterioles, excepting a few spots, is actually going to increase our total peripheral resistance, okay? And so we can see here how all of these responses are working to increase that mean arterial pressure, to correct that original error signal, which was hypotension. So via all the mechanisms that we just described, I'm going to increase total peripheral resistance. That's going to increase my mean arterial pressure. I'm going to increase my stroke volume. That will also help to correct or increase my mean arterial pressure. And then I'm going to increase my heart rate, which is also serving to correct that mean arterial pressure.